Hello viewers, welcome back to the course on scientific computing using MATLAB. So, in the previous lectures we have discussed the iterative methods for solving the linear system of equation. So, in the previous lecture we have discussed that how we can make the MATLAB code for the Gauss-Jacobi method. So, in today's lecture we will try to make the MATLAB code for Gauss-seidel method. And we know that in the Gauss-seidel methods that the method is convergent if eigenvalues, the modulus value of the eigenvalues should be less than or equal to 1 or the spectral radius, that is rho h, that should be less than 1. So, and the rho h we know that this rho h, where h is the convergence matrix. So, this one we can delete, it should be strictly less than 1. So, and now in the Gauss-seidel method we know that the h will become minus L plus D inverse u. So, in this case we will try to find that what is the our convergence matrix. Now, if we want to find the rate of convergence, so rate of convergence of iterative methods to solve the system A x is equal to b. So, find the rate of convergence. So, rate of convergence is given as that is equal to minus log and then spectral radius, because the spectral radius we are taking. So, that is the maximum value we are taking. So, if you see from here we can write this as, I can write should be less than 1. So, if I take the maximum eigenvalues, using that one we will find the spectrum, and I know that if the Gauss-seidel method is converging, that then the eigenvalue, the maximum eigenvalue will be less than 1. So, that is why the negative sign has been taken, because this quantity is less than 1. So, whenever I take the log of this one, that will be negative. So, just to get rid of this one I will take the negative sign from here. So, that is the rate of convergence of any iterative methods. It may be a Gauss-seidel, it may be a Gauss-Jacobi and other iterative method, then the rate of convergence is given by this formula. And in the code we will try to make, so we will introduce all this in the MATLAB code. We will introduce that how we can calculate this convergence matrix, then how we can calculate the rate of convergence for a given initial condition. So, let us move to then, so let us move to MATLAB to code Gauss-seidel method. So, let us move to the MATLAB. So, let us start doing the code for the Gauss-seidel. So, as we have done in the Jacobi method, so I have also made the Gauss-seidel method. This is for you. So, we can do it here. Now, it is same as I am defining the function that x is equal to seidel a, b, x naught and tolerance. So, in the previous one we have changed the name to Jacobi. So, now it is a seidel, Gauss-seidel method. Other things are same, that A is the matrix which we are going to solve, that is n cross n, b is the right hand vector and x naught is the initial approximation of the solution, and the tolerance is that how much accuracy I need for the finding the solution of the system. Now, this is the b. So, I find the length of b, that is n. Now, from here I define a vector that is with the 0 elements. So, this is the dimension n and the column 1. So, it is a column vector. So, you can write from here that this is the column vector. Now, I start with the iteration. So, that is initial value 0. I just take the error is equal to 1 just to start the process. Now, the display I show that the initial guess is whatever the initial guess I give. So, that will be x, I will put that one is the x old is equal to x naught. So, x naught is coming from this from the function where this function has been called. So, this x naught will go and it will save into the x alt, and if I want to display this one, so I will remove these semicolons. Now, this will be displayed on the screen. Now, I will go to the while loop. So, in the while loop I will go from here that this is the, if the error is greater than tolerance and iteration is less than 100, then we should enter into this one. So, if any one of is false, then we will not move to the while loop. So, error should be greater than tolerance and iteration should be less than 100. Now, from here if I go inside, then I will go from j from 1 to n. Now, what will happen in the Gauss-seidel method, that the first value, that is the first equation of the system, will find out the value of x. Suppose I have a the solution as x y z in 3 by 3 or x1, x2, x3 up to xn in n by n matrix, then x1 will be calculated same as the Jacobi method. So, this will be j is equal to 1. So, x nu 1 will be bj, that is 1 because j is 1 here, minus a j. So, j is 1 and these are the matrix from 2 to n multiply by x old, whatever the initial approximation I have given. So, that will be multiplied by this one, and then the whole divided by xjj, the coefficient of x1. So, that is the first point in the matrix. So, this will be calculated, and then the last one j is equal to n. So, I know that in when I take j is equal to n, then the new updated value will be used to find out the x nu. So, that is why I take x nu j, that is equal to bj, and then the same matrix a j from 1 to n minus 1, and then see from here that I have taken the x nu. So, this is the x nu. So, whatever the solution we are getting from the previous equations we are solving, that j is equal to 1 and j is equal to 2, 3 up to n minus 1, that all solution will be used here and then divided by ajj. So, this and these conditions we have to calculate separately, else means other than these first and last, we will find out the x nu j is equal to bj. So, this is the value we are going to use. So, what is going to happen if we split the matrix into two parts? So, the matrix below the diagonal elements will be calculated this x nu, and above the main diagonal it will be used with the x alt. So, whatever the same thing we have done. So, we will find out the bj minus aj, and then all the columns from 1 to j minus 1, I will use the updated value, that is x nu, minus aj and j plus 1 to n, because I have to leave the value on ajj. So, after that all the values above the main diagonal I am using the old value. So, that is from j plus 1 to n, and then the whole things will be divided by ajj. So, in this case we have to split the whole while loop and then for the for loop into three parts, when j is equal to 1, j is equal to n, and other than that. Now, this is the end of if loop and this is the end of for loop. Then I will find the error. So, this is the norm I am taking. So, x nu minus x old, and I am taking the maximum norm. So, that is the error I am taking. Then after this I will, whatever the value we are getting from this x nu, I will use this x nu to update my old value. So, there that is this x nu will go to the x old. Now, iteration will be increased by 1. So, earlier iteration was 0, now it is 1. So, after one iteration, whatever the solution you are getting, you will get this. Now, this is I have written this one to find out that how the accuracy and how the solution is approaching to converge. So, I have displayed only two cases when my matrix is 3 by 3 or my matrix is 4 by 4, because other than it is very difficult to display it on the screen. So, if n is equal to 3, I will print at iteration. So, x1, so I suppose I have 3 by 3 system. So, my solutions are x, y, z. So, I put x at this iteration here, y at this iteration and z that iteration, and this is the error I am finding. So, I will put this here as iteration x old one, because all the solution is going to this as a vector. So, that first component will be I am treating as a x, then the second component I am treating as a y, and the third component I am treating as a z. So, this is the z I am finding, and in the last I am finding the displaying the error also, and that is the backslash n is the new line. So, this will end, and if n is equal to 4, the same thing is happening, except the last one I will take that as a w, and then solution will be x old 4, and this is the error. So, I will display this one on the screen, and this will be updated at each iteration, and that will be displayed in the screen as in the form of a table, and then I will end this while loop, and then x is equal to x nu, because I have to send back this x output. So, this my x nu, after all this iteration, my x nu will go and it will save in the x, and this x will be returned to the system or returned to the code from where this function has been called. So, this is the function we have made for seidel method. Now, I will want to use this one. So, let us I will use MATLAB code we have used for the Gauss-Jacobi. So, this is my clear all CLC. Now, in this case I will start with the matrix. This one. So, what I do, I will take iterative method, and let us take this system. And for the Gauss-Jacobi also we have discussed that this is going to be diverging. So, let us do this one. Now, after doing, I will make the code, because from here to here I have used this one for the Gauss-Jacobi, because this is the Gauss-Jacobi. Only change we have done is that here we are calling with the Gauss-Jacobi. Now, I am doing the same thing for the Gauss-seidel. So, I have made this code applicable for all the Gauss elimination, Gauss Jacobi and Gauss-seidel. So, in this case, here I am taking 3 by 3 system. So, this is 3 by 3 system. So, I am taking the initial condition as 1 1 0, and this is the dash, means the will be a column vector. The tolerance I am taking 10 is to power minus 5. Now, I will call the function x is equal to Gauss-seidel from here. So, this is the input I am passing. Then after that it will give me the x. So, I will show that the display, the solution of the given system is this one. Now, what I want to do, I want to find the convergence matrix. So, that is the convergence matrix. N is the length of B, L is the left matrix, D is the diagonal matrix, U is the upper triangular matrix. So, L is the lower triangular matrix. So, I will putting the value of the given matrix into the corresponding lower diagonal or upper triangular matrix. So, it is I am putting for loop I from 1 to n and j from 1 to n. Now, if I is less than j, it means I am putting that if I is 1, then if I is 1, then j will move from 2 to n. Okay. So, 1 is I is less than j, then I will getting the values as a upper triangular matrix. Okay. So, now if I is equal to j, then this will saved in the diagonal matrix as a diagonal matrix, and this is the else value. So, if it is not this or not this, then whatever is left, that will saved in the lower triangular matrix. Okay. So, this is the way we can split the matrix A into the lower triangular, upper triangular, diagonal matrix. Now, from the Gauss-seidel method, I know that my convergence matrix is minus inverse L plus D multiplied by U. Now, the display the eigenvalues of the corresponding matrix, I find the eigenvalue of this matrix. So, that will show the eigenvalue. Then I find the spectral radius. So, spectral radius I am finding from here, and I call that a spectral rad. So, that is what I am doing, I am finding the eigenvalue, then I take the absolute value, because the eigenvalue may be complex also. So, in that case I will find out the absolute value of that, and then I am finding the maximum of all. Now, I am from here I am displaying that the spectral radius and the rate of convergence of the given method is spectral radius will be this one, and minus log of the spectral radius, that is the rate of convergence. So, let us try to run this one. So, I will run this one, and so let us see what will happen. So, from here if you see, it started with the iteration number 1, then x iteration, y iteration, z iteration. So, this is my initial solution, and the error is this. Then it is keep increasing, then at the iteration number 2 the solution goes to minus 14, then minus 161, and you see that the value is going to be infinity, minus infinity in this case, and the error if you see, then the error is going to be increasing and going to be infinity. So, in this case after 100 iteration I stopped my program, and then this is the solution, and in this case I can see that the method is not converging, it is diverging. So, this for the given system of equation our method is diverging, and from here you can also see that if you find the eigenvalue, then it is coming almost 10 eigenvalue. So, the eigenvalue is coming 10, because if this system is going to converge, then we know that the eigenvalue is going to be less than 1, the modulus of that eigenvalues. So, this is the first one we have taken. Now, I will change this one, and then I will take this system. So, this is also 3 by 3 system I am taking, and then I run this one. So, let us see what will happen. Now, from here this is my solution. So, the initial guess I started with 1 1 0. Now, after the 7 iteration you can see that my solution is this x is converging to 2, this is converging to 4, and z is converging to 3. So, that is my system, the solution of this system. And then if I find the eigenvalue, so eigenvalue is coming 0. So, 0 eigenvalue means this matrix is singular matrix, then its value is minus 0.1, and this is the maximum eigenvalue, this one. So, the maximum eigenvalue is 0.1250. So, that shows that the spectral radius is this one. So, using this spectral radius, so that is my spectral radius, and you can see that the rate of convergence is very high, that is 2. So, with this help with this Gauss-seidel method, I am able to find the solution in the 7 iteration only. Now, from here you can see that what will happen if I change the initial approximation. So, let us try to change the initial approximation. Suppose I take x 0 is equal to 1 0 0, or what will happen if I take all the zeros, then let us see what will happen. And if we see from here, then if I take 0 0, then the solution is still converging to this one within the 7 iteration, and the same eigenvalue definitely will come, but in this case the iterations are similar, the 7 iteration. So, I told you that you can choose any initial condition, whatever the initial condition you want to choose. Now, suppose I put it 0 0 0 and then 1, then let us see what will happen. So, in this case also if you see 0 0 1, the same initial condition means changing the initial condition, but the number of iterations is same and the rate of convergence same. So, this is the way we can find that how for the different initial condition our method is converging, because from here we can see that if I take the convergence matrix, then the eigenvalue of convergence matrix is less than 1, the modulus of that one. So, and the smallest the value, the faster the method will be. So, in this case the eigenvalue, the maximum eigenvalue is 0.125. So, that is why you can see that the order of convergence is quite high, and that is second order method in this case. So, this is the 3 by 3 system I have taken. Now, let us try to take the another system. So, let us take 4 by 4. So, 4 by 4 system, but the initial condition I have to change. So, this is the initial condition 4 by 4. So, I will take this one as a, because that vector initial vector should be of 4 components. So, this is x, y, z and w, and the tolerance I am not changing, I am keeping the same tolerance. So, my system is now 4 cross 4. So, let us run this one, and from here if you see, now I have started with the 4 by 4 matrix, and the initial approximation of the solution I am starting with 1 1 1 0. Now, you can see that iteration number 1, this value is at the initial point, then after the iteration, each iteration this is converging very fast. Even after the 5th iteration you can see that it is going close to the root, and after few iteration, that is the iteration that our solution is now reaching to the tolerance. So, in this case my x component has 0.49, so 0.5 is the value, 0.27 minus of 0.52 and 0.37. So, that is this one, and error you can see that my error is 0.0002. So, it is less than the given tolerance. So, that is why we stopped here, and now from here you can see that the eigenvalues I am finding. So, these are the eigenvalues I am finding, and from here you can see that one eigenvalue is finding is 0, another is the complex eigenvalue, x component is this and y component is this. Now, again, and we know that the eigenvalues, if they are complex, they appear in a conjugate form. So, that is the conjugate of this complex number, and then I am getting the another real eigenvalue, that is 0.1645. So, now from here I take the modulus absolute value of this one. So, after getting the absolute value, I find that the spectral radius is coming this, because this is the E value I am getting. So, E 1 is 0. So, I just check that what will happen, absolute value of E 2 is point, see this is the 0.2191. So, that is the absolute value of this. So, this is, and then using this one I find the order of rate of convergence. So, rate of convergence in this case is 1.51. So, because here the eigenvalue, the spectral radius has increased, in the previous case it was 0.1, now it is 0.21. So, the it is going close to, means as compared to the previous one, this value is greater. So, that is why the order of convergence or the rate of convergence has decreased from 2 to 1.5. So, this way we can find the solution for 4 by 4 system. Now, the same thing I can take. Now, what I do, I will reduce the tolerance. Now, I am keeping the same initial condition, but I am reducing the tolerance. So, let us see what will happen. So, in this case, now you can see that the tolerance I have decreased by one factor only. Now, the number of iteration has reduced from the previous one. So, it is now it is 7 iteration, and the solution is accurate up to 4 decimal. So, this is less than 0.0 10 to the power minus 4. So, now this is my error. So, number of iterations is reduced and this is my solution. Now, from here you can see that because this is not going to change with respect to the initial condition or the tolerance. So, that is not going to change and the rate of convergence will be same, that is 1.5. Only the change comes with the number of iteration that. So, in this case the number of iterations are same. Now, what will happen, let us see if I change the initial condition 1 0 1 0. So, in this case 1 0 1 0 the same number of iteration we are getting now 0.7 or the iterations are 7 and the error has reduced from in the previous one it was 0.003, now it is 0.002. So, the solution is this one. So, that is my approximate solution after 7 iteration. So, in this case the solution is converging, because you can see from here that after 3 iteration you will get the knowledge of that what will be the solution. See the power of this method, that even after 3 iteration you can see that the solution is converging toward 0.49, this is converging to 0.27, this is converging to minus 0.52 and that is 0.37. So, even after 3 iteration you are able to see or guess that where our solution is going to have to lie. So, that is the power of the Gauss-seidel method. Now, so in this case I may, so that is 4 by 4 system we have taken. Now, let us take another system. So, let us take another 4 cross 4 system. So, I will write in front of you. So, let us take the matrix A, that is equal to, suppose I take the matrix 1.2, then 2.3, then 0 and then I take 1. So, that is the first row I take, then I take minus 0.1, then 0, then 0.5, then minus 1.5. So, this is the another row I am taking, then I take the another row 0, 1, 0, 0.2. So, this is the another one and now I take the last row. So, last row is 0.25 minus 0.3, 0, 0. So, let us take this system where the matrix is this and then I take the right hand side vector. So, B I am taking 1, 0, 0.3, 1.5. So, let us take this one, I am just taking the randomly. So, let us try to solve this one. So, I run this one and then see what will happen. Now, from here the matrix, it is coming that the matrix is singular and so you can see that even after the first iteration this solution X is giving and the Y, Z and W they are coming not a number. So, let us change this matrix, or maybe I can take this initial condition, change in initial condition. So, the same thing, so let us see. So, the same thing is happening now. It means that this system is not solvable with the help of Gauss-seidel method. Maybe I can change this matrix into the simpler one. So, I will take 1, 1.2, 3. So, let us take 3 by 3 matrix. So, I just put 3 plus 1 4 and 5.2. Then I take 1.1 0 and 2, and then another I take 4 minus 1 and 3. So, let us take this system 3 by 3, and I just on the right hand side I take the summation of all the elements in the row. So, 1 3 4 5. So, I take 5.2. Then the next one I take 1.1 0 and 2. So, it is 2 plus 1 3.1, and then the last one is 4 plus 3 7 minus 1 6. So, let us take this one. So, its answer should be 1 1, and I take this one as 0. So, let us take this and try to find the solution for this. So, let us take the previous case. Let us see what is happening, because it may happen that I have now it is giving the solution for the given matrix. So, in this case the solution is there. Actually, maybe I am not taking a matrix with a diagonal dominancy. So, let us so I am taking this. So, let us change this one to diagonal dominancy. Because our matrix, if the matrix is diagonal dominant, so let us take this as a 3 and this is 1. So, I take 1.1 and then 2 and then 0, okay, and then I take this 3 and then I take 4 maybe. So, in this case this is a diagonal dominant 1.1 to 0. So, that is the matrix, and 3 minus 1. So, maybe I can take this one. So, let us see what will happen. Yeah, so now it is giving the solution. So, after the 12 iterations you are getting the solution. So, that was the problem, because I have chosen a random matrix and that was not diagonally dominant. So, from here you can see that the solution is going to be 1, close to 1, and the matrix was singular. So, it is 0. So, both two eigenvalues are 0 basically, and this is 0.51. So, if it is going to be very large as compared to the previous cases, so in this you can see the rate of convergence has increased to be even less than linear value. So, it is 0.6 value. So, now we will stop here. So, today we have discussed the MATLAB code for Gauss-seidel method, and with the help of Gauss-seidel method we have tried to solve the system 3 by 3 system or 4 by 4 system, and we also found that the system is not diagonally dominant, then it may or may not converge. So, in that previous case it was not converging, but when we make the matrix as a diagonal dominant, then it was giving the solution in the 12 iteration. So, in the next lecture we will continue with the other problems. So, thanks for viewing. Thanks very much.